So now I'm going to discuss the Euclidean algorithm by means of an example, and you'll see that the method will apply in general. So let's suppose that we want to find the greatest common divisor of these two integers, 3536 and 1275. So in effect, what we're going to do is repeatedly apply the division algorithm in the following way. So first of all, arrange things so that the larger of the two integers appears first. And as I've remarked before, we can always take the two integers to be positive. If the two integers are the same, if these two integers were the same, then of course their greatest common divisor would be equal to either one of them. So now what we're going to do is we're going to take the larger integer as the dividend and the smaller integer as the divisor, and this ends up, by the division algorithm, we get a quotient, in this case of 2, and a remainder of 986. Now what I claim is that any number which divides those two, any common divisor, will also be a common divisor of those, and conversely, because suppose I have a number that divides both of those. That means it divides 3536 and 1275, but because 986 is equal to a multiple, namely 1 times that minus 2 times that, then any number that divides each of those will divide 986. So any divisor of those two, any common divisor of those two, will divide 986. And of course, any common divisor of those two will divide 1275 because that's one of them. It was the smaller of the two integers we began with. Conversely, if I take any divisor of 1275 and 986, then because it divides 1275 and 986, then from this equality, we see it must divide 3536. So the upshot is that any divisor of those two is a divisor of these two, and any divisor of those two is a divisor of those two. So in particular, the greatest common divisor of those two is the same as the greatest common divisor of those two. And what we've done is we've started off with two integers, a bigger one and a smaller one, and we've found that the greatest common divisor of those two integers is the same as the greatest common divisor of the smaller one, and the remainder after we use the smaller one as a divisor. So we also know that the remainder is always less than the divisor. So that means that these two integers are less than those two. More precisely, this is less than that, and this is less than that, and that will always be true. So let's go to the next step to find this greatest common divisor. So now we're looking at the greatest common divisor of 1275 and 986, same as here. So once again, we use 1275 as the dividend and 986 as the divisor. And this is the equation we get from the division algorithm. If we divide by 986 into this number, it goes once, and the remainder is 289. So what we have is that the greatest common divisor, by exactly the same argument as before, the greatest common divisor of these two is the same as the greatest common divisor of those two. So once again, we've now got a smaller pair of numbers. More precisely, that is smaller than that, and that is smaller than that. And we can now just keep repeating this process, and I've written down here all the steps. At the next step here, clearly if something divides 289 and 119, it divides 986, and if it divides 986 and 289, it divides 119, and that's the essential point in showing this equality. And finally, if I now look at 51 and 17, then 17 in fact divides evenly 3 times, and the remainder is 0. Now, we've seen the way that these numbers are decreasing, that in particular this remainder here is less than this remainder is less than this remainder, and all the way down. So eventually, since the remainders keep decreasing, we must eventually hit 0. In this particular case, when the remainder is 0, that means that this divides that evenly, so that the greatest common divisor of 51 and 17 is indeed 17. So now we just go back up, and we have the greatest common divisor of that is 17, so hence of that is 17. The greatest common divisor of that is 17, and hence the greatest common divisor there is 17, all the way up until we see the greatest common divisor of that, of the original pair, is 17. So just writing down a little bit more carefully, the argument there is that the remainders decrease and they're bigger than or equal to 0, so they must actually equal 0. And if you look at it carefully, the line 1 remainder, that's here, which was 986, is equal to the line 2 divisor, so that must be bigger than, because of the division algorithm, the line 2 remainder. And then the line 2 remainder here is equal to the line 3 divisor, and that's bigger than the line 3 remainder because of the division algorithm, and so on. So the remainders are always decreasing, and they must eventually go down to 0, just as I said before. And then, as we see, the last line quotient, which is here, the quotient in the last line, which is the remainder in the second last, or penultimate line, is the required greatest common divisor.